In this video, we'll see how we can take the nScope data from the app and view it in Python with kind of finer resolution because we'll be plotting the data directly instead of trying to look at it in the image that the app provides. I've built my pulse detection circuit, and here's how it's wired. We've got our raw phototransistor voltage going to channel 1. I've high-passed it at 1 Hertz and plugged that into channel 2. I've amplified it by a factor of 1,000, and that's viewed by channel 3. And then I low-passed it around 5 Hertz on channel 4. So for your specific circuit, depending on where you put your finger and how still you can stay, these numbers might be a little different, but that's the rough block diagram. Let's switch over to the nScope app. And here we see channel 1, so this is the raw phototransistor voltage. When I put my finger down, you can see that now I'm blocking the light from my room, which got rid of the fuzziness. And if I kind of jiggle my finger around, we see it move up and around. But if I stay still, we get a nice constant voltage, just a little bit above -5 volts. So somewhere in there is a tiny signal with my heartbeat in it. We can't amplify it now though because it doesn't have a mean of 0. So we're going to look at channel 2, which is the high-passed version of that voltage. Same exact signal. I can move my finger and we see it wiggle. But now the high pass has removed the 0 Hertz or DC component of the signal. Now we can amplify. So that's channel 3. And here's my amplification of 1,000. So it just blocks everything. We're just getting so much noise that we don't get to see it. But if I filter it on channel 4 with a low pass filter, we can see my heartbeat. So that's just the smoothed out version of the blue signal. So looking at this, it's hard to tell exactly what the voltages are. That's why we want to see the raw data and plot it in another program. To get the raw data, you go to Capture and Save CSV. But before that, you do that, there's a few caveats. The first is that if you want to view channel 1 data, only channel 1 has to be on. If you want to view channel 2 data, channel 1 and channel 2 has to be on. So if you want to see channel 4 data like we do here, all 4 channels need to be on. So I've got all 4 on. And then if I said stop right now, I'd be able to save the data, but I'd only get the data up to this blank area. So I want to use the single function to grab a whole screen's worth of data. And when you're collecting your data, you probably don't want to talk like I'm doing right now because that's probably messing up my heartbeat a little. Okay, so now that it turned from single automatically to stop, I can go to Capture, Save CSV, and then select a folder where it's going to be saved to. That'll be the raw data itself. Only do that. Say Capture, Save CSV. And I'm saving my data into a folder that I called Python because I'll be doing all my work for the class in that folder. And let's take a look at that file. I'm going to open it up in a text editor called Visual Studio Code. We'll talk about that more in a second. A CSV file is really just rows of data separated by commas, and every row is a new data point. So the first row shows us the titles of the row. So we have time and then the voltages for the channels. And then we can see that there were a lot of data points saved on that screen. So we'll get much finer resolution by opening this up in another program rather than just viewing it in the nScope app. Now, when we start editing this data in Python, I like to remove this first line because it's not numbers that'll confuse Python. Note there's a bug here. It says channel 0 through channel 3 when really we were plugged into channel 1 through channel 4. That's fine. So I'm just going to delete that and save it. That'll make it easier to open up later in Python. How did you get Python installed on your computer? I'll let you figure out how you want to get Python. Here's where I got Python from. So I like to install Anaconda. Anaconda installs Python plus all of the most common, really popular libraries like Matplotlib and NumPy and things that we need. Python by itself doesn't come with the libraries that you need to do those. I like to do my editing in Visual Studio Code, which is an IDE or Integrated Development Environment. It's just a fancy text editor. And the nice thing about it is that it has plugins. It has this plugin for Python that hooks up to Anaconda so that we can run the code directly in Visual Studio Code. You might prefer to use Jupyter Notebook or Spider. Here I'm going to show you how to do it with Visual Studio Code. So let's go back to Visual Studio Code. We've already looked at the CSV file. That shows us the raw data. Let me show you my Python code that opens that up and plots it. So Python is tab-based indentations. So anything that happens inside of this with statement has one tab, and then anything that happens inside this for statement has a tab. There's no semicolons at the end, like you find in MATLAB. Other than that, it's kind of similar to MATLAB. To be able to use libraries, we have to import them. So I'm going to use a library called CSV that allows us to open CSV files. That's where our data is. And then I'm importing matplotlib, the pyplot functions that lets us generate plots. And I renamed it to PLT so I didn't have to write matplotlib.pyplot every time. So the first thing I have to do is I have to get my data out of the CSV file. I can use the function open to open my CSV file, and I'll call that file f. And then I can make a variable called reader that returns the data from the file. And then I can read out every single row in the file. So for every row that's in this file, I will grab the first number that's in that row. Now append it to my list T. So T was initially blank, so the first time through, I get the first element in the first row and put it into T, and I put the second element and put it into what I called raw, and then HP, and then unf, and then data. And that stands for, so this is my time array, this is my raw data from the phototransistor, this is the high pass data, this is the unfiltered data, and then finally this is my filtered data, the heartbeat itself. So this runs through every single row in my CSV file, and there's just an amazing number of those. Let's try to scroll down really fast. There are 4,800 data points in this file. So these are very long arrays. Then I can print the length of those arrays, just so I get some verification that this worked. That'll print into my terminal window. And then I plot all the data, and I made a couple different plots. So the first plot, I plot time versus my raw data in black, and time versus my high pass data in green, time versus my unfiltered in red, and then time versus the filtered data in blue. I set up some bins so that I know that my axes are plus and minus 5 volts and things like that. And I give this a title. This is all of my signals. And then I show just the raw phototransistor voltage, just the high pass voltage, and then the filtered and unfiltered versions. To run my code, I would go to terminal, new terminal. That will open up in the bottom of Visual Studio Code. And then I would type py for Python, and then the name of the file I'm trying to run, which is this file opencv. And if I type op and hit tab, it'll autocomplete for me. And I can hit enter and it'll run. Now my screen capture doesn't end up capturing the little pop-ups that show the graphs, so I made a PDF instead. So we'll look at that PDF. Here it is. So here's the first graph that pops up when I run this code. It shows me all of the voltages simultaneously. So this is essentially the exact same data that the nScope app showed, but now I've got -5 to only the maximum, so the minimum to the maximum voltage. So it kind of zoomed in correctly. And it showed me that I had 6 seconds worth of data, and I had 1, 2, 3, 4, 5, 6, 7 heartbeats in 6 seconds, so I could count my beats per minute if I wanted to. The black line, that's the raw voltage from the phototransistor. The green line, that's the voltage from the high-pass filter, same thing as the black, just no DC component. The red is the amplified green, and then the blue is the filtered red. So that's pretty neat. If I look at just the raw phototransistor voltage, so we can see that it had a mean of -4 volts because there just wasn't a whole lot of light bouncing on my finger. And then we could see the peak-to-peak voltage change due to my heartbeat. And it was going from -3.98 to -4.04. So this was changing by 0.06 volts. And it had a mean of -4 volts. So the high pass was to remove the mean of -4. The amplification was to go from a peak-to-peak of 0.06 volts to something like 1 or 2 volts. And then the low-pass filter smoothed it all out again. So we could see, we couldn't exactly zoom in the nScope app like we could in Python to see this raw data like this. That's why it's useful to do in Python instead. Notice also that the data is kind of, I don't know, striated, right? We see that there are discrete levels of voltages that the nScope has been able to read. So in between negative 4 volts and negative 4.02 volts, there's something like, I don't know, 10 levels here. So the resolution that the nScope used was something like 2 millivolts. So obviously, we don't want to read a signal that is this small on the plus or minus 5 volt scale because we're just not getting a whole lot of different voltage levels when we read with the nScope. It just doesn't have the resolution. That's why it's nice to use our filters and our op amps to make the signal as big as possible on the plus and minus 5 volt scale so that we take advantage of the full range and resolution that the nScope provides. We'll talk about this stuff later, and when we start talking about the appropriate level of how fast should we sample and at what resolution. So here, this was our raw data. Here's the data after the high pass. So this was channel 2. We can see it's pretty much the exact same data. It's just been shifted up by 4 volts. Notice it doesn't have a mean of 0. That's actually, I think, an nScope bug. The nScope doesn't think 0 is really 0. So this probably does have a mean of 0. Okay, then we amplify and filter. So the red is the same thing as the green, if you'll believe that, but it has the same level of noise, but it's just bigger now. So we multiply by, in this case, I don't know, it was 100 or 300 or 1,000. And then the blue has been low pass filtered. And we still have this raw data in Python. So the next thing we're going to do is we're going to write some loops, and we're going to go through every single data point and try to identify the peaks, and then automatically count the beats per minute.